Welcome to the fifth of our Setonix migration training modules, where we will look at how to submit, run, and monitor your computing jobs. What has changed when it comes to running jobs on Setonix? We will go through changes to the accounting model, changes to the Slurm configuration, how to modify your existing Slurm batch scripts to run on Setonix, and then review how we can monitor and manage submitted jobs. As with our other supercomputing systems, we use Slurm to run and manage jobs on Setonix. The process is very similar to, say, that on Magnus, but there are some important differences which we'll go through in the following slides. The biggest change is that the compute nodes on Setonix have 128 physical cores across 2 sockets. Correspondingly, we have moved to support shared node access by default. Unless exclusive access is requested, your job may share a node with jobs of other users. This means that if you do not need to use all of the cores on a node, you can use less of your allocation. But it also means the performance of your job may be affected by other activity on the shared node. We've also made changes to the way the Slurm partitions have been configured and implemented a hard cap on system usage at 150% of your project allocation. We'll start with the changes to our accounting model that accommodate the new shared node access. At Pawsey, our accounting is based on service units. One service unit corresponds to an allocation of 1 CPU core for 1 hour. For example, a full day's worth of a single node on Magnus constitutes 576 service units. That's 24 cores multiplied by 24 hours. On Setonix, though, there are many more cores per node, and that same allocation would constitute only 4.5 node hours. On Magnus, the smallest granularity of a job is a node. If your job doesn't need to use all the cores on an allocated node, a portion of your total project allocation is essentially wasted. With the much larger number of cores on Setonix nodes, this would be even more wasteful. So on Setonix, as mentioned earlier, we have a shared allocation model by default. You can make a resource request that comprises only a subset of a node's cores or a fraction of its memory. Associated with each core is its proportion of the node's total memory. If your request requires, for example, 3 cores for running tasks, but 4 cores worth of memory, it will consume 4 service units per hour and not 3. It's always the larger fraction of the core usage or the memory usage that is relevant. On the left here, the diagram represents a request for half of a node's cores, but 2/3 of its memory. On the right, we have a request for 1/3 of the node memory, but for 2/3 of its cores. In both cases, the request corresponds to 2/3 of a node for accounting purposes. With exclusive access, which can still be requested on Setonix, all of the node's resources are available to your job. You can explicitly pin your processes and threads to specific cores, and the performance of your job will be more predictable. The use of all 128 cores will be charged against your project allocation. With shared access, you will have less control over the particular assignment of cores to threads. Other jobs may share the node, and your task may perform less predictably. But only the subset of the node that you requested will be charged against your allocation. As things stand, core assignments in shared node access are not optimal, but this will improve in future system updates. You can and should use the Pawsey account balance tool to check how much of your project allocation has been spent. Once you have used all of your allocation in a quarter, you may still submit jobs, but they run at a lower priority. However, once 150% of your allocation has been used, no more jobs will be run until the next quarter. Now let's move on to the changes to the Slurm partitions. The use of the various Slurm partitions has been simplified. In addition to the work and debug partitions, the copy, highmem, and long partitions are also available directly on Setonix. We've also removed the trailing queue from the partition name, saving you valuable keystrokes. In total, there are 6 partitions on Setonix: the work partition, the debug partition, the copy partition, the high memory partition, the long runtime partition, and the partition dedicated to ASCAP radio telescope operations. We will go through these in detail in the following slides. The work partition is the bread and butter partition, where most of your compute jobs will be run. It is the default partition, but we do recommend that your scripts specify our partition explicitly. Each node in the partition has 128 cores and 230 gigabytes of available memory, and jobs in this partition are limited to a runtime of 24 hours. If you know your job won't require 24 hours, please do request less. It will allow your jobs to be scheduled more easily. The debug partition is intended to be used for testing, debugging, development, and for running short and interactive jobs. The nodes have the same configuration as the nodes in the work partition, but the maximum job time is limited to 1 hour. Again, if you do not need a full hour, please request less. The copy partition is specifically for data transfer operations. It should be used for transferring data to and from the Acacia object store, exporting data from scratch to systems outside Pawsey, and for migrating data from the previous generation group and home file systems to Setonix. If you have data on the old Scratch file system that you wish to migrate, you will still have to use the Zeus copy queue partition, where the Setonix Scratch file system is mounted as new Scratch. The maximum job time on the copy partition is 48 hours. The nodes in the copy partition have only 32 cores each and 89 gigabytes of available RAM. By default, a job won't have access to all of the core's associated memory. If you run into issues with insufficient memory, you should add an explicit memory request directive to your Slurm batch script. Some jobs may require more than the 230 gigabytes of RAM available on the work partition nodes. You can use the highmem partition for these jobs, where each node has up to 980 gigabytes of available memory. Jobs submitted to the highmem partition should explicitly request the amount of memory they need, up to this limit. As there are only 8 nodes in this partition, availability may be somewhat limited. If it is possible to reorganize your computation to require less memory per node so that it can run at the work partition, it is likely to be scheduled in a more timely manner. Lastly, we have the long partition, which is specifically for jobs that require more than 24 hours of runtime. There is still a maximum runtime of 96 hours per job, and as with the highmem partition, there are only 8 available nodes, which may lead to some contention. We strongly recommend restructuring your tasks to fit within the work partition if that is possible. Each job that you submit has a corresponding quality of service. Jobs with a higher quality of service will be scheduled more promptly than those with a lower. By default, each job has this normal quality of service, but you can request a high QoS for up to 10% of your allocation. Once you've used all of your quarterly allocation, your jobs will be assigned a low quality of service. And once you've used 150% of your quarterly allocation, any submitted jobs will be assigned the exhausted quality of service and won't be scheduled until the next quarter. The highest quality of service is reserved for critical operational tasks and for urgent critical research, such as, for example, work related to the initial COVID-19 response. To summarize, on Setonix, the partitions you'll be using day to day are all available on the one system, and we've removed the queue from their names. We now have a hard limit on usage over your project allocation of 150%, and by default, jobs on these partitions have shared instead of exclusive use of nodes. Now we'll take a look at how to update or create Slurm batch scripts for Setonix. Slurm batch scripts are shell scripts that contain particular Slurm directives that describe the nature of your resource request. When you submit a job to Slurm, it will use these directives to dimension and schedule your job. Each script has essentially 4 parts: a hashbang line that invokes a shell, a series of directives, some environmental configuration, and then finally the execution of your job with srun. Each Slurm batch script should have the following directives: an account directive, which associates the job with the project, a partition directive, which selects the partition to run the job, node, task, and CPU directives, which describe where and how many parallel tasks will be run, and how many cores each will require, a time directive, which describes the maximum runtime of your job, and lastly, if required, a directive requesting exclusive node access. If your job will require all or nearly all of a node's resources, you should request exclusive access with the corresponding Slurm directive. In some instances, you may also want exclusive access to a node for performance reasons, for example, to secure the full memory bandwidth. When porting scripts to Setonix, you should check that your required modules are available and update, if necessary, their versions in your script. You should also check for any hard-coded paths in the script. As there is no group file system on Setonix, instances of the mygroup environment variable, or paths referencing /group, will need to be changed to refer to the software or Scratch file systems. Any OpenMP environment variables should also be set in this section, and you can refer to our OpenMP documentation for more information. For launching the job with srun, there is usually no need to provide any further options. srun will use the information provided in the Slurm directives. Some workflows will require srun commands that use only a subset of the requested resources, which is where you may need to use the -n or -c options. More details can be found in our documentation through the link in this slide. We'll go through a few example Slurm batch scripts corresponding to different parallel programming models. Our first example is an MPI parallel job running 512 tasks with 128 tasks per node. This corresponds to one task on every core on 4 nodes. The exclusive option is provided because we will be using the entirety of each node's resources. In the diagram here, we have grouped cores into groups of 8 corresponding to their shared L3 cache. In the second example, we're running a single OpenMP task with 128 threads. It will allocate each of the 128 cores to a thread. And again, because we use all of the node, we supply the exclusive option. The OpenMP environment variables direct the OpenMP runtime to place its threads accordingly. This third example is of a hybrid MPI and OpenMP job. 2 tasks, each comprising 64 parallel threads, are allocated to each of 4 nodes for a total of 8 tasks. We have here a shared node example of an MPI parallel job comprising 64 tasks on a single node. The n tasks per socket directive indicates to Slurm that we want all 64 processes assigned to the same socket, which will limit interference from any other jobs on the node. We give srun the -m option to properly distribute the tasks across the cores in that single socket. And in this example, we have a request for 8 cores for an OpenMP parallel job in a shared environment. Another user has allocated only 6 cores, resulting in the job being spread over 2 different chiplets. If instead that user had used 8 cores, the job would be fully allocated on the second chiplet. This is an example of a situation where shared node access may impact the performance of the job. Lastly, we have an example of a job with an explicit memory allocation. Here, despite only requesting 1 core to run a single task, the requested 57 gigabytes of RAM corresponds to a full quarter of the node. In summary, on Setonix, we have 128 cores per node compared to 24 on Magnus. Each node has 230 gigabytes available instead of approximately 60. And in addition, we have shared L3 cache domains for each chiplet of 8 cores, compared with a single cache domain per socket on Magnus. For this next session, I will pass the presentation to my colleague, Chris.
Thanks, Sam. And so this next section is called Submitting and Monitoring Your Job on Setonix. So we have here on the right, this flowchart, an overview of the process of scheduling a job. And it has a number of steps. The first step is to prepare. So it's always good to make a directory where you're going to have all of the input for the job and the job script. It's also a good idea, although optional, to try testing your script, usually in the debug partition. You then submit your job and monitor it as it works its way through the queues and runs, and finally review the output and transfer any data off of the Scratch file system. So to look at these steps in more detail, before submitting a job, some good things to do is to make sure that you have the correct versions of any software available in the /software file system. Make sure that you have a working directory for the job in the Scratch file system, And we recommend keeping a copy of your Slurm batch script with the working directory. And so that way, if you're coming back to look at it, you know exactly what it was that you submitted to Slurm. And it's a lot easier to debug things when they don't go as expected. We also recommend having a copy of sort of template batch scripts, which we don't recommend keeping on Scratch because they may get purged after 30 days. And so these sort of template Slurm batch scripts should live in your software directory and then get copied out to that working directory as needed. You should also prepare your input data. So see the modules 2 and 6 for information on how to stage data onto the Scratch file system, either from your local machine or from the Acacia object store. And you may also need to create directories for the output data if needed. So we do recommend testing your batch scripts, particularly if it's the first time that you've been putting them together. And so the way that you do this is to prepare a test case for your software. And this can be done in a number of ways. Often some good approaches to use is to reduce the number of time steps or the execution time, or maybe have it run across less data or less parameters to search. You can reduce the number of nodes needed for the job in terms of reducing the resolution of the simulation you're running, but this is not as recommended because it can sometimes change the performance of the job and make it harder for you to estimate how long the full job is going to take. So you should perform a short test run that takes maybe about 5 to 10 minutes in the debug partition. And you can do that by just submitting your batch script. So you can either go into your batch script, which you can see here in this first line, and actually edit the partition directive to put it specifically into the debug queue. Or you could also override the Slurm directives. So you sort of leave the work partition in the job script. And then when you SBatch it to the scheduler, override the directive using the -- partition command line argument to SBatch. We also recommend doing a little bit of benchmarking to identify how well your workflow scales. So this might mean running a few short tests for using a different number of cores. And as Sam mentioned earlier in the presentation, for optimal performance, we recommend using multiples of 8 cores on the system. So using multiples of 8 cores for your scaling test works quite well. You can also test with the exclusive node access if you want to have predictable performance for the partial node jobs. So the next step is to submit the job. And you can see here, we're seeding into MyScratch. We recommend submitting your jobs from the Scratch file system for the best performance. You can see here we have a test shell that we're going to be submitting. You can also check the state of the system using sinfo. We can see here that we have 303 idle nodes in the work queue, as we've run this command prior to the migration where it's quite quiet. You may find from time to time that there are a number of idle nodes in the work queue, but you're still sitting there in the queue waiting. And this can be because the nodes are draining ready for a large job to launch. And so they're only going to be idle for a short period of time before a very large sort of MPI job starts running. So that can be the reason why there's idle nodes there and your job's not running immediately. But then you can submit your script using SBatch, and it will provide a job ID back to you at the command line. And then once the job's finished, you can see if we've typed a ls to list the directory contents, you can see a slurm dash, and then that same job ID as the output, which will happen when you complete the job later in this process. You can also use interactive sessions. We don't recommend doing this for large scale work, particularly if you've requested tens or hundreds of nodes. Then all those nodes are sitting idle while you're typing commands and wasting your allocation. So it's something that you really only do for small test cases when you're doing things like debugging or compiling, pre and post processing, or possibly running some GUI applications. You use the select command to obtain the interactive session. You can see here in this example, we're using select in the work partition, and that will put you out onto the node that you've requested. You can provide all of the Slurm directives that you would normally put at the top of your Slurm batch script as command line arguments to alloc. And then once you've run this command, you end up out on the node as if you were sort of inside the environment of your job script. You can type commands interactively. So in terms of monitoring your job through the queue, initially when you submit it, it may be waiting or pending for the job to complete. And if you use the --me argument, it will only show you your jobs, which can make it easier to discern your jobs from others in your project. One change that we have made moving to Setonix is that jobs from other projects will no longer be visible, which will hopefully make it easier to see your jobs in the queue. By default, the SQ command shows basic information such as the job ID, user, and accounting. You can, if you look at the manual pages for SQ, customize the output. And so that's something, if you have specific things you'd like to see there, you might want to look into. There's also the SPRIO command, which shows what makes up the priority of your job. So we can see here for this particular job, the priority is made of a combination of the quality of service and the fair share. While it's running, you will still see it there in the queue. The PD pending state will change to an R for running. And depending on the nature of your job, if you have a job that is actively generating files on the file system, if you are you can then look at the file system and see if those files are starting to appear as you expect them. Once the job's complete, you can look at how the job went using the S account with the -J flag and then providing the job ID. And the other thing that's a good idea to do is to look at the job output, that slurm.out file, to see if there's any error codes or error messages. So to review the job efficiency, we have a command in Slurm called ceph, and it will actually provide a little bit of information around how much of the resources on the node that your job used, and that can be useful in getting a sense of how your job is using the system. It's a good idea to review the output of your job and make sure that it did what you thought it did. Check that all the files that you expected are present. Check that the size of those files is the size that you're expecting. Make sure all the checkpoints that you were looking for were completed, and having a look at the data to make sure the output is what you think it should be. If things haven't gone right, then it's a good idea to check your Slurm batch script, check permissions on directories, software installations, and input parameters. And often, hopefully, there's error messages that provide some information on what's gone wrong that will help you work your way through figuring it out. Finally, it's always important to transfer files off of the Scratch file system, particularly given it has a 30-day purge policy. And so possible destinations for that data can include the Pawsey Acacia object store, as well as your institutional data storage facilities, or your laptop or USB hard drives and the like. So we've covered some details on how to do that in module 2, the supercomputing file systems. And for working with Acacia, definitely check out module 6, using data throughout the project lifecycle. So that brings us to the end of this module. Thank you for watching. If you can find more information in our Setonix migration guide and supercomputing documentation on our documentation portal, there's the other migration training modules that you should definitely have a look at. And if you have any issues send us a help desk request through our service desk, and we can help guide you through the migration process. Thanks for watching.